This video is about another fixed point iteration method called the Newton-Raphson method. So in this method we're going to have another iterative formula. In this case we're going to be generating x values by using an x value, xr, and subtracting f of xr, so that's substituting xr into our f of x, divided by f dash of xr, where f dash of xr means the derivative of f of x evaluated at xr. So depending on what our f of x is, we'll be able to make our own Newton-Raphson formula. So using the one that's given in the coursework booklet, we've got that f of x is x cubed minus 3x plus 1. So in my formula, the numerator, f of xr, is this with xr in place of all the x's, and my denominator is this f dash of x with my xr in place of all the x's. This is just differentiating the f of x to create f dash of x. So x cubed, when you differentiate it, you get 3x squared. If you differentiate minus 3x, you get minus 3. And if you differentiate plus 1, you get 0. So using my iterative formula, I'm going to need to have a value for x0 to begin. Now I take my x0 to be a value of x that's close to the root I'm looking for. In this section of the coursework I have to solve the equation, so I'm actually going to find all three roots. So I'm going to use x0 is minus 2, I'm also going to do the whole process using x0 is 0, because this root is quite close to 0, and I'm going to use x0 is 2, because this root is quite close to 2. My x0 has to be an integer on either side of the root, so I could actually have used x0 is 1 instead of 2. Although we'll see later, sometimes the method doesn't work, and in fact it ends up that if I try to start with a 1, it's not going to work. Be aware of that when you're doing your coursework to make sure that you can actually solve the equation with this method, so you can find all three roots using the method. I'll just show you where this iterative formula comes from, so that you don't think it's some kind of magic formula created by the wizards Newton and Raphson. This formula depends on creating some tangents to the curve y equals f of x, created at certain points. The first tangent is drawn at a point where the x value is an integer quite close to the root. So if I'm trying to find this root here, I'm going to use x0 is 2, and at this point here then, I'm going to create a tangent to the curve. This point has coordinates x0, f of x0. The equation of the tangent is just the equation of a straight line. Now I know a point on the line, I've got this point, x0, f of x0, and I know the gradient of the line. I can substitute these into the y minus y1 equation. The gradient of the line is just going to be f dash of x evaluated at x0. So I've got y minus the y coordinate, f of x0, equals the gradient, f dash of x0, multiplied by x minus x0. There's another point that I know that's on this tangent though. I know this point here, x1, 0. x1 is the place where the tangent cuts the x-axis, and in fact this is going to be our next approximation to the root. So x1 is a value that's a closer approximation to the root than x0. Now if I substitute x1 and 0 in place of x and y in the equation, then I'll see that I've got an equation that I can rearrange to end up with x1 on its own in terms of x0. So if I divide by f dash of x0, then just add x0 to both sides, what we'll see is that I end up with an equation for x1. So it's x0 minus f of x0 divided by f dash of x0. I'm going to repeat the process now. So this time I'm going to use x1, and at the place on the curve where x is x1, draw a new tangent, and where this tangent cuts the x-axis is going to give me the value x2. So the equation of this tangent can be found similarly to the previous one. So I've got y minus the x coordinate, and this time I'm using the x coordinate of x1, and that's going to be f dash of x1, so the gradient of the curve at that point, x minus x1. The y coordinate is f of x1. I can also substitute in the values for y and x using that y is 0 and x is x2, which is the coordinates of this point where this second tangent cuts the x-axis. Now if I just rearrange, then I can get a value x2 in terms of x1. And it's exactly the same formula as for x1 in terms of x0. And in general, what I've got is the Newton-Raphson iterative formula, that to create an x value, I use a previous x value minus f of that x value divided by f dash of that x value. I can do the calculations in Excel quite easily. I need to type in my value of x0 first. In this case, I'm starting with 2 because I'm trying to find this root, which is quite close to the integer 2. I then need to type in my Newton-Raphson iterative formula into cell B2. Here's my Newton-Raphson iterative formula. Everywhere I see an XR, I'm actually going to click on the cell above and it will appear as a B1 in the formula. I then click on the bottom right hand side corner of the cell and get the thin black cross, click and drag, and it will copy the formula down the cells, and you'll notice each time it's going to use the value from the cell above to calculate the value that appears in the next cell. So x0, the value 2, will be substituted into the formula to produce the value of x1. That's substituted into the formula again to give the value of x2, substituted again to give x3, and so on. So over here we see what happens. So we've got the first value of 2, and then when 2 is put into this formula, we end up with 1 2/3, and if we keep going, we see eventually it seems to have converged to the root. We need to do a change of sign check as before, so we go 0.000005 above and below the root and just check for a change of sign. So we can see here that doing f of x for these two values, one of them is negative, one of them is positive. We've got a change of sign, so we can say that our root is x is 1.532009 with a maximum error of 0.000005. This process works because of the tangents that the formula represents and the values within those tangents, and this was described earlier. You need to illustrate this looking at x0, x1 and x2, where x0 is your integer. The first tangent is drawn to the curve when x takes that value. Where this tangent cuts the x-axis gives you your x1 value. Then another tangent is drawn to the curve at the place where x is x1, and then where this tangent cuts the x-axis gives you your x2 value. You'll need to produce an illustration like this in your coursework. To illustrate this method using autograph, you start by entering y equals f of x, and your curve should be displayed. If you click on your curve to highlight it, it will go black. When it's gone black, so it's highlighted, if you right-click, you'll get this list of options, and you see Newton-Raphson iteration is one of the options. You click on it. When you've clicked on the Newton-Raphson iteration option, you get this box asking you to set it up. So you need to type in the value of x0. I'm looking for this root here, and I've chosen the integer 2. So I've typed in x0 is 2, and then I'll press this button. So far I've only pressed it once and I've got my first iteration shown. If I keep pressing this button, it will begin to make the sawtooth diagram that you need to use to illustrate your work. So when you've finished with your illustration, make sure that you remember to label the curve with y equals f of x, label your values x0, x1, x2. You may be able to label x3 as well, it depends on how quickly it's converged to the root. And you should label these tangents to make it clear what's in your diagram. You could also label the root that you're trying to find. Make sure as well you label the x-axis and the y-axis. Autograph does actually label these for you, but sometimes people crop their pictures and the x and the y disappear, which is not good. In your coursework, you also need to show an example of where the Newton-Raphson method fails to find a root that you're trying to find. So in this case, I'm actually using the same equation. You'll probably use a different equation. But I'm going to try and find this root. And I could quite sensibly decide to start using x0 is 1, because it's an integer that's quite close to the root. But I encounter problems because, in fact, there's a minimum point here, a stationary point. So f dash of 1 is 0. The gradient of the curve at that point is 0. Now remember where f dash of 1 goes in the iterative formula. Here it is. So I'm going to try and do something and divide by 0. Now, if you try and do that in Excel, typing in the iterative formula, it's going to give me an error message because we can't divide by 0. Not even Excel can divide by 0. So this method is going to fail to find this root. I'll illustrate this in my coursework with a diagram like this one, and by showing my attempt at doing the calculations in Excel and showing the values substituted in place in the iterative formula. I can create curves that will have this problem with the Newton-Raphson method quite easily. What I do is I come up with a curve that has a minimum point right on the axis. So actually this is just a repeated root that's sitting there. So in this case I used x minus 3 squared as one of the factors of my f of x. So I've got a repeated root at 3 and that's a minimum point. Now if I just subtract a bit from this equation, in this case I just did minus 2, the whole curve moves down a bit. So I no longer have this integer root, you see it's moved here, and I no longer have my repeated root at 3, but I've still got a minimum point at 3. So now, if I was trying to find this root over here, or this one in fact, I could try to use x0 is 3, but the Newton-Raphson method would fail to find the root, because in the formula we'd be trying to divide by 0, and we can clearly see that the tangent to the curve is not going to cut the x-axis to create a new value x1. So here's an overview of everything that you need to do. So start by stating the equation that you're trying to solve. Notice you are solving it this time, finding all 3 of the roots if it has 3 roots. And this is a different f of x from the one that you used with the other 2 methods. You need to show how you've differentiated your f of x to get your f dash x, which goes into the Newton-Raphson iterative formula, and you need to display your iterative formula, where instead of writing f of xr, you actually write yours in full, xr cubed minus 3xr plus 1, or whatever it is that you've used. And you need to show a graph of this, pointing out the roots that you're trying to find. Make sure your graph is fully annotated. It should look a lot like the ones in the coursework guide. You need to show your calculations in Excel. Make it clear what your starting integer is. And you should probably have 3 starting integers here. You only need to illustrate this for one of the roots, but you need to show the calculations for all 3 roots and show that you've checked for change of sign for all 3 roots. You need a zoomed in graph showing the tangents, and that's all annotated as I showed you earlier. You also need to describe how the iterations are performed and refer to your Excel table, what happens with the calculations, and refer to the graph and what happens with the tangents. So you need the sign check, change of sign check for all 3 roots, and explain why you needed to do this. You need to state what your root is. Some people forget to do this. They highlight the roots in the Excel table and think they've solved it. You actually need to state all 3 roots and state what the error is that goes with each one. So you do all of that for all 3 roots. And then you also need to show that the method sometimes fails. You need to do the same sorts of steps again and include a graph with a tangent drawn to show that the method has failed to locate the root. You can use the coursework guide to check that you've done everything, and your work should look a lot like the bits in the coursework guide. And finally, here is the mark sheet, the assessment sheet. You'll notice this method has 5 marks. So you get 1 mark for finding one root and then another mark for finding all the roots. So if you've done a cubic with 3 roots, that means finding all 3 roots correctly gets you 2 marks. Your illustration, as long as it's done correctly and all fully annotated, will get you 1 mark. There's actually a whole mark in this section for doing the error bounds. By the point that you get to here, you should have been doing error bounds for all your roots anyway, so you'll be used to this and hopefully you'll automatically get that mark. And finally, an example of an equation where the method fails to find a root, despite having an integer close to it, with the illustrated explanation, that gets you the final mark. And the cats are just there because I've been told that if videos are on YouTube, they're supposed to have cats in them. So there you go.